Yeah, thank you, Professor Miley. And for this one, I'm gonna tell you how plasmonics works for the condensed matter nuclear fusion reaction. And so in the last meeting, back to 2 years ago, or 2016, ICCF-20, I presented a plasmonic effect or electromagnetic field enhancement effect for particle type or shape of metal materials or nanostructures metals. And calculated the enhancement factor, which is the ratio of the electromagnetic field intensity under the existence of the metallic subject, particularly around the surface, compared with the original electromagnetic field in the absence of such metallic objects. And then, at that moment, showed a relatively high intensity enhancement up to 1,000 times, particularly for noble metals such as gold, silver, copper, and for shorter wavelengths, maybe aluminum also works well. And then, for example, palladium, nickel, titanium, which are used particularly for this field, condensed matter nuclear fusion. We calculated the enhancement factor is around a couple of tens times higher than the original field. So this enhancement effect may be useful for the enhancement or increase of the reaction rate, because such effect can focus energy at particularly points of the surface of metals. And then, although I, at that point, calculated the enhancement factor for spherical shape of object, metallic object, for simplicity, but theoretically it's shown that if we used sharpened, curvatured particles like needles, which is called lightning rod effect in plasmonics, as well as nanogaps, the field is highly confinement around sharpened surface and also in between a tiny multiple object of metallic surfaces, so like called nanogaps. And then this plasmonic boosting effect may have been unknowingly or unconsciously produced in the experiments reported so far in this field, particularly for the electrolysis type ones, because they apply voltage to induce electromagnetic field. So by such plasmonic focusing effect, the energy of the incident electromagnetic energy is highly enhanced around a particular region of the reactive or active points. And then this time I investigated the possibility of this plasmonic effect particularly in the case of planar metal surfaces, which have been used for experimental samples in this field by many groups, as well as ourselves, as I presented this morning. So what I calculated is the field enhancement factor, whose definition is the intensity ratio between the fields around the object and those in the absence of the object. So, or the original incident field, as I mentioned previously, And this factor represents how much energy can be concentrated from the incident electric or optical power, so that this effect can be used both for electrolysis type of experiments as well as laser incident type of experiments. So here is the calculation method, so which is based on the very basic Maxwell equations, and we can simply write down the electromagnetic field in the form of, I separated the representation into the magnetic field across the schematically two-dimensionally described like this, and we have a vacuum or a dielectric material space on top of a metallic object, and then we have an interface of the dielectric and the metallic object, and then each of those materials are represented by their dielectric functions, epsilon 1 and 2, and the magnetic field is described like this, as well as the electric field like this. And the energy flux in the x direction is the parallel to this interface, is calculated by the pointing vector of those fields, and then gonna be wrote down like this. And the energy dissipation of the surface plasmons can be calculated simply by taking first order derivative of the energy flux like this, and then on the other hand, the energy flux into the metallic surface from the external field, which couples into the surface plasmon mode, is described like this. And here, the ESP represents the electric field on the metallic surface, and then from the original field, and then, oh no, this is the surface plasmon mode, and this is the original one. And then by taking the energy conservation rule in the steady state, those two are equals to each other, so that we can make this equation. And then finally, we reach the targeted electromagnetic field enhancement factor, which is the ratio of the plasmonic surface plasmon mode field intensity relative to the original incidence of the field in this way. So basically, this factor is simply calculated by using the dielectric functions, which is dielectric constant dependent on the wavelength or frequency of the original field in this way. And by the way, the reference work I used, which was a paper like 30 years ago, used an approximation for noble metals, because the authors calculated only for silver and gold at the point, so that they can easily make an assumption that the absorption loss, which is represented by the imaginary part of the dielectric function of the metal, is negligible. However, in this field, we deal with palladium, nickel, titanium, those relatively lossy materials. We cannot ignore the lossy factor or the imaginary part of the dielectric function. So I took into account such factor and fully, without any approximation, calculated this factor. And here is the result of my calculation. And although I only had frequency or wavelength range of like optical or around the visible range of the electromagnetic field, but calculated the field enhancement factor around a couple of tens times for the represented or conventionally used metals, palladium, nickel, titanium, for this field. In both cases, in vacuum or air or deuterium, as well as aqueous phase in light water or heavy water. And then here we see a certain degree of field enhancement is attainable even for the common metals, not only novel metals, but also for the common metals for us, which is a good indication. And some experiments may have already unknowingly or unconsciously benefited from this kind of effect. And here I provide a qualitative explanation of this field enhancement mechanism. So probably some people may be skeptical, oh, you enhance the energy, but what about the energy conservation rule, or what about if can it be a steady state? But the answer is no problem. And for example, if we did not account for the electric or optical energy conversion or coupling into the surface plasmon mode, the incident energy will be just reflected at the metal surface or partially absorbed. In other words, the energy will just come in and go out with the speed of light with no interaction with the material. So spatially uniform energy density is given in the system. However, a part of the incident energy will be converted into the form of propagating or localized surface plasmon modes. Propagation happens on the surface, or namely the interface between the dielectric circumstance and the metallic surface, or sometimes localized surface plasmon mode is generated, particularly for the nanostructured or particle isolated type of metal materials. And then such effect provides us a longer time to stay around the metallic surface. So larger energy density on the metal surfaces than the far field. Far field means the original incident field without any metallic object. By the way, this situation is realized without the contradiction under the steady state and energy conservation, as I mentioned before. You can imagine this situation, for example, for the car traffic on the freeway, and we see that particularly around the toll gate, where we pay for the traffic charge, lot of cars are stacked. But this situation is on the steady state, and for example, a couple of minutes later, 1 hour later, days, this situation always happens. So, and the car flow, no cars gonna be disappeared or generated at some point. So the energy or the flux is conserved. So this theory stands in the aspect for both energy conservation and steady state situation. And then let's think about the contribution of such plasmonic effect for the cold fusion reaction. And if the spatial density of the reactive sites and the nuclear reaction probability had been sufficiently high, the given incident energy would have been almost perfectly absorbed and converted for the reaction excitation. And namely, the electromagnetic enhancement effect we present in this work would have hardly contributed to the reaction rate. However, as we all know, in reality, the situation is not like that for many reported experiments, because we know the reaction rate is never sufficiently high, or the density of the reactively active sites in the material is high. That's relatively low, probably only around the surface or in some vacancy or defect sites. And then, therefore, the enhancement of the supplied energy density around the nuclear reaction sites would increase the reaction rates by providing a larger opportunity and a larger amount of energy to be absorbed and then utilized for the excitation. By the way, it should be noted that our calculation presented this time is only based on the Maxwell equations, which are pretty basic theory in physics, and involves nothing exotic or physically novel. So I'm pretty much confident that there is no doubt for this field enhancement effect I present. And thinking about the surface situation or status of the metal material we use in our experiments, and the point is the roughness for the plasmonic coupling, because the far field original incident field cannot be easily coupled to a flatly or atomically smooth metallic surface. So no coupling occurs for such perfectly smooth surface. In that case, only regular surface reflection happens with a small amount of absorption. So sub-wavelength scale surface structures, depending on the original field, are needed for efficient coupling, surface plasmon coupling. Sometimes random roughness is also fine. Not necessarily periodical structures are fine, because many researchers in plasmonics uses like grating or prism attenuated total reflection method, but such fancy structures are not necessarily required. Only random roughness is fine. And intrinsic or electrolysis induced or etched micro nanoscale roughness on the metallic surface possibly existed in the past reported experimental works. So there may be still some surface plasmon electromagnetic enhancement effect even for the metal plate type of samples, not only for nanostructures one, as I presented last time. So it is highly possible that the reason that many of the successful experimental reports have been have been conducted by using samples with micro or nanostructures is partly attributed to the plasmonic enhancement effect, because such surfaces with some nanostructures can easily couple the far field or original incident field into the plasmonic propagating or localized mode, which provides a high enhancement of the energy density, which may cause some or support the nuclear reaction. Another evidence for this speculative plasmonic boosting effect is that there have been a number of successful experimental reports with the application of alternative AC or modulated electrical bias. Some may have used this. type of not only DC bias rather than the stationary field, which may have unknowingly excited the surface plasmon oscillation so that the enhancement effect can be realized. This is a summary of my work. I investigated the plasmonic enhancement effect, which can increase the optical power density or electrolysis ones on planar metallic surfaces. And then I calculated the enhancement factor as a couple of tens times of energy density enhancement for the conventional metallic materials in this field. And then I'd like to mention that I never believe that this plasmonic effect is the only clue or key to solve the mystery of the reaction realization in this field, but only a part of the keys which are eventually multiplied. So probably effect A, B, C, D, E, and then only when accidentally those factors are realized that the nuclear reaction may happen. So I think this plasmonic effect is just a factor to be multiplied with other factors, which probably at this point not consciously understand, but we are gonna tackle to figure out all of the factors in the future. And so yeah, thank you for your attention.
Thank you. We can have time for a few questions.
I should like to congratulate we run into this problem of surface quality many times in our experiments, and I feel that this is a blessing, 10% and the curse 90%, the surface quality, because you just cannot maintain it. It's really, I think it's a burden on our back, but I'm really glad that you brought up this problem. It is very important and completely neglected by the experimental community. Thank you.
Thank you.
Hi. I was wondering if you looked into maybe investigating whether lattice defects in the metal had an effect on the coupling.
Oh, say that again.
Lattice defects? Did you investigate that at all in your metals that you investigated?
Oh, you mean the roughness? Oh, what's it? What? Oh, lattice defect. Yeah, probably for the field or wavelengths which are regularly used in this field is not, the wavelength is not that small. So probably the lattice defect or point defect may not necessarily affect this effect. But if we use, for example, very high frequency for the bias voltage, such as small scale defect or modulation in materials may influence.
Cool. Okay, good. Thank you.
One last quick question.
Yes, on the plasmon concept, how does it couple to a nuclear energy source? What is that coupling? You know, we have Peter talking about phonons and nuclear vibrations. How does this plasmon couple to that particular, if it does, that particular mode of energy release from the nucleus?
All right, I haven't figured out the particular mechanism to for the coupling you mentioned, but I believe this is one of the boosters to for the energies to supply the two atoms get approach or get close to each other. So the reason why many people use electrolysis is to supply energies, electromagnetic energy, onto a specific reactive points of the material, and then I meant that energy density is enhanced by a couple of tens or 1,000 factor. Oh, yeah.